Good morning, I am Nalini. In this lesson, I am going to discuss about asymptotic notations. I am going to discuss about these topics: time complexity, best, worst, average case analysis, asymptotic notations based on growth functions. These are the textbooks. Actually, we have four textbooks mentioned in our syllabus. The first these three textbooks covers algorithm topics well. You can follow any of the book. I suggest you to follow the first one, Codman. This is a very good book. Shagini also you can follow for fundamentals of algorithm. Anyone wants to refer more examples and exercise, you can go with the Dr. Sridhar Design and Analysis of Algorithms book. So before discussing about asymptotic notations, first we must know what is meant by analysis of algorithm. So analysis of algorithm is a technique that measures the performance of an algorithm. It is actually based on two factors called space and time complexity. So the eventual goal of analysis of algorithm is to compare different algorithms to solve the same problem. So time and space complexity plays a vital role to analyze the performance of an algorithm. So generally there is always more than one way to solve a problem. So we need a method to compare the solutions in order to determine which one is more optimal. So we have a method to choose the optimal solution is called time complexity. So time complexity specifies the amount of time taken by an algorithm to run. Uh, Based on the size of the input. You have to note down one thing, that this time complexity, it is not the execution time of a machine, right? Okay, next is space complexity. So the space complexity defines amount of storage required to run by an algorithm. We will discuss how to calculate time complexity and space complexity in the upcoming slide, right? So to calculate a time and the space complexity, we have a method. It is called a step count or frequency count method. So using this method, you can calculate time as well as space complexity, right? So we have some assumptions to how to calculate this step count or frequency count method. Usually each line of code must be considered to calculate the time as well as space complexity, right? So the basic assumptions are here. The usually for each line of code we will allocate 1 unit of time. So there is no count for open and close brackets, means flower brackets. We are not allocating any amount of time for open and close curly braces, flower brackets, right? And we are allocating 1 unit of time for assignment, arithmetic, logical and return statement. And also we have to follow two general rules. The first one is called drop lower order terms and drop constant multiplier. This we will discuss how to implement in algorithms. So take this example. See here, you have two examples. Take the first example. In the first one, here you have integer a equal to 10 plus b. Okay, here you have one assignment operator and here you have one arithmetic operator, right? So as based on our assumptions, we need to allocate 1 unit of time for assignment and another unit of time for arithmetic operations. Totally this statement needs 2 unit of time, right? 2 unit of time. And you take this second statement, k equal to a star 5. So this assignment statement requires 1 unit of time and this multiplication statement requires 1 unit of time. Total this also required 2 units of time. So total amount of time needed by this algorithm is actually 4 unit of time, right? This is a 4 constant 4, right? So this can be replaced with our standard constant functions called big O of n. So the total time complexity for this algorithm is big O of 1, right? right? You can also you can see the second example. Here also you have if n greater than 100, a equal to a plus 10. This statement also requires 2 unit of time, one for assignment and one for arithmetic operation. So the else part also you have one statement a equal to a plus 5. This also requires 2 unit of time. So the total time taken by this algorithm is always as like previous example, this algorithm also gives some constant time. So this also can be replaced with the constant time functions big O of 1, right? So but take this third example. In this example you have a for loop, right? So for integer I equal to 0, I less than n, I plus plus, right? So 1 unit of time needed for this assignment operation and another unit of time needed for this comparison, right? Comparison operation. And here also you have an individual statement a equal to a plus I, right? So we are allocating 1 unit of time for this assignment and another unit of time for this arithmetic operation plus. So this also takes the constant time, 2 units of time, right? So when you come to here the for loop, this for loop executes n plus 1 time, right? Why n plus 1 time means, even though here we are mentioning integer I equal to 0, I less than n, but this loop going to execute for n plus 1 times, means this loop is going to execute one more time for the false statement, means it takes one additional extra time to check the false condition also. So the total time complexity for this algorithm is n plus 1 plus some constant term, right? Based on the general rule, we must drop the constant terms, and right. Okay, so we can take so the runtime for this algorithm is big O of n, means it gives linear time. This can be replaced with our standard function big O of n. So one more example, sum of a comma b, return a plus b. Here you have one return statement and here a plus b you have an arithmetic operator. So total time required for this algorithm is 2 units of time. This is also constant time. This can be replaced with a constant function, standard function big O of n. Here I am mentioning the detailed step count for this algorithm. Sum of list a comma n, total equal to 0. So the cost for this statement requires 1 unit of time, and for I equal to 0 to n minus 1, the cost required for this step is 2 unit of time, because 1 for assignment and 1 for this comparisons, to 2 unit of time. And the cost for this statement total equal to total plus a requires 2 unit of time, 1 for assignment operation, 1 for arithmetic operation, so total 2 units of time. And the return statement takes 1 unit of time, right? These are the cost for this statement, each individual statement. And we need to calculate number of times, how many number of times these statements are going to execute, right? Number of times required for this first statement is only 1. For the second statement for loop, it takes n plus 1. As I said earlier, to check the false condition also, the loop executed for one more time, extra one time, it takes extra one time, so n plus 1 time. And total equal to total plus ai, this statement requires 2 unit of time and it is executes for n times, because this statement available within this for loop, right? So next return total, this also takes 1 unit of time. Number of time this statement is going to execute for only one time. So total time complexity for this algorithm is 1 plus 2, you multiply cost and number of times, right? 1 into 1, 1 plus 2 into n plus 1 plus 2 into n, that is 2n, plus 1 into 1, that is 1, right? So 1 plus this 2n plus 1 can be expanded, right? Like 2n plus 2, right? So total 2n plus 2n plus 4n plus 2 plus 1 plus 1 equal to 4. So total time complexity for this algorithm is 4n plus 4. Here 4n plus 4, this 4 is constant term, this is constant multiplier 4n In the 4n, 4 is constant multiplier, so these can be replaced with some constant term c. So cn plus c dash. So total time required for this algorithm is big O of n, right? This gives linear time. This algorithm gives linear time. It can be represented with the standard function big O of n. Okay, so the first algorithm gives a big O of n, big O of 1 time. The second algorithm gives big O of n. The third algorithm, for example, T sum of matrix equal to an square plus bn plus c. We know how to calculate matrix. Usually, generally, we will use two for loops to calculate matrix, right? So the two for loops takes n square time. So the total time taken by this algorithm is big O of n squared, right? Means we are replacing this time complexity with our standard function big O of n squared. So all these times times algorithms time complexity can be plotted on a graph. T sum of list and T sum of matrix. The T sum requires constant time big O of 1. T sum of list, this algorithm takes big O of n time. The T sum of matrix algorithm, this takes big O of n squared. So among all these algorithm, T sum gives the takes the minimum time big O of 1, and T sum of matrix, this algorithm takes maximum time big O of n squared. We can also see two more examples using step count method. Algorithm sum of a comma n, the same algorithm, sum equal to 0 and I equal to 1 to n, sum equal to sum plus ai, return sum, right? The step count for this flower bracket is 0, as I said earlier, because we are not allocating any unit of time, with any amount of time for this open and close curly flower bracket, right? Sum equal to 0, it takes 1 unit of time. For I equal to 1 to n, this takes n plus 1 time. Sum equal to sum plus ai takes n time. Return sum, this takes 1 time. This also takes 0 time, right? So total time complexity for this, when you add sum up everything, you will get 2n plus 3, right? Next, calculate space complexity also. For the first sum equal to 0 statement takes one word to store the variable sum, and it takes for I equal to 1 to n, this takes one word for each I and n, and sum equal to sum plus ai, this takes n words for array A. Total space required for this algorithm is n plus 3 words. So total time required for this algorithm is time complexity for this algorithm is big O of n, because we have to neglect constant as well as constant multiplier. So we can get a big O of n for the space complexity also. You will get big O of n time. You can see the next example, algorithm add a comma b comma c mn. Here in this algorithm I am using two for loop, right? So this first for loop takes m plus 1 time. The second for loop takes n plus 1 time. It means this for loop is going to execute for n plus 1 time. We have outermost for loop also, so this can be multiplied with the outermost for loop time. So m into n plus 1, and this statement takes mn, because this statement available within this innermost for loop, so this can be multiplied with m cross n. So total time required for this algorithm is 2mn plus 2m plus 2, right? Here I gave explanation also how this m plus 1 and how we are arriving this m plus 1, right? You can also refer. So the total time required for this algorithm is 2mn plus 2m plus 2. Okay, so in this way we can calculate the time as well as space complexity of an algorithm, right? So in the next upcoming session I will tell you how to calculate time complexity based on growth functions, means asymptotic notations, right? Thank you.